In this experiment, you will be looking at how to characterize the stoichiometry of various reactions, but also of mixtures of substances. And so we'll start with a mixture of a substance, and we'll use reactions to help us determine the stoichiometry of the reaction and therefore the stoichiometry of the substance mixture. And just as a brief reminder as we get started in discussing this topic, the stoichiometric relationship in a reaction is given by the coefficients of the species in the reaction. And so I've drawn this ball and stick model of a reaction to help us think about what the coefficient means in a visual sense. But this is a commonly used reaction to show stoichiometry. So we have an N2 molecule, and it is reacting with 3 H2 molecules, and then forming 2 molecules of ammonia. So I'm going to write out ammonia as NH3. And we have 2 of those molecules because we have 2 nitrogens atoms that can form molecules. And if we were given this in an unbalanced way to begin with, you could figure out how many there should be in the products based on, logically, if 1 nitrogen binds to 3 oxygens, you need the ratio to be 1 to 3 for the reactants. And the only reason we end up with 2 products is because the reactants are gases that are molecules of 2 atoms. All right, so that's kind of the basis of stoichiometry. So this ratio of the number of particles allows us to also characterize the ratio of masses involved. And one of the more typical experiments we could use to determine the stoichiometry involved in a reaction is called a titration. You may have done a titration before in the past, but this leverages the stoichiometry of solution concentrations. And so the key, though, is that the reaction is based in moles, not in molarity, but solutions are based in molarity. So we're going to do most reactions in chemistry in a solution format. So the concentration is very important because the concentration we can use as a proxy to figure out the number of moles that were used in the reaction, and that's based on knowing the volume. All right, so that's kind of a little bit more background, but molarity is moles over liters. We should have hopefully covered that up to this point. But in a titration, you have your burette and you have your flask. In the burette, we put a solution that we call the titrant, and the titrant is at a standardized known concentration. And as we add solution, we can measure the volume difference based on the lines. So difference in volumes. So that will tell us what volume was added, and we can use the volume with the molarity to figure out the moles according to the molarity formula. That's what the titrant is used for. So whatever is in the titrant will react with whatever is in the analyte. And that is the key concept. And this reaction is stoichiometric. So I'm just going to write stoich for that. That is kind of the key there. So it could be a 1-to-1 ratio, could be a 1-to-2 ratio, etc. we know the ratio of moles, then we can determine based on how many moles of titrant were added. That will tell us how many moles of analyte must have been in the flask. So analyte is unknown concentration most typically, but known volume usually. So we would say, okay, let's put 10 milliliters. It could also be known mass. We put 20 grams of solution or 20 grams of solid, sometimes even. It depends on the context of the titration. A lot of times these reactions will be acid-base reactions, but there are other types of titrations as well. And in this experiment, we will be doing a redox titration, which means an oxidation reduction reaction is used in the titration for the lab for this experiment. Okay, so the first part of the experiment is going to be titration, so the context we just discussed. We're going to be starting with a sample of sodium percarbonate. Normally, this Na2CO3 would just be called sodium carbonate, but when it has peroxides attached, we call it sodium percarbonate. And when this is initially formulated in the manufacturing facility, they will make the ratio of molecules of hydrogen peroxide to sodium carbonate usually would start out as 2, but degradation over time leads to your N being somewhere between 1 to 2, typically. And so that means that you might have some of these with 2 attached, some of these with 1 attached, some with none attached, but you can get an overall average to determine what the average value of N is in your sample. And so that's what we want to do. We want to analyze our solid sample of sodium percarbonate to figure out how much hydrogen peroxide per sodium carbonate molecule is present. And so we'll leverage multiple reactions to do this. The first one is going to react the hydrogen peroxide. So that's the part we're trying to determine how much is present. So hydrogen peroxide will oxidize. You'll learn in the second portion of the course what oxidation means, but it will oxidize iodide in the presence of acid. So this is here just to represent acid. You're going to add sulfuric acid, I believe. And so these iodide, I- ions, become triiodide ions. And triiodide is easily visualized by adding a starch indicator. It's literally just potato starch or any kind of starch. Triiodide will bind to it and create a really dark blue color. The other product is water, but we're going to ignore the water because the key is this triiodide. So once this is formed, we can turn it blue by adding starch. And this becomes our analyte in our actual titration. So we're going to set up like a mixture in the beginning to get reaction 1 going. We're going to have our solid, dissolve it, add triiodide and acid, or add iodide and acid to the solution. It should all react based on however many moles of H2O2 we had present to actually do the oxidation step. We'll let our hydrogen peroxide be our limiting reactant there. We'll create I3. The solution will turn dark blue because we have starch in there as well. So our analyte starts out dark blue, and then we start working on reaction 2. Reaction 2 is actually to use up the triiodide and reduce it back down to iodide ions. And we can do this with a solution of sodium thiosulfate. And the sodium is not involved, so we'll just call it thiosulfate in this reaction. And when triiodide is reduced to 3 iodide ions, our thiosulfate gets oxidized to SO4 or S4O6 2-. And we're not going to worry about that. The key is how much of triiodide, how many moles of triiodide must be present if our titrant moles are known. So because we know the concentration of our thiosulfate solution in the burette, we can determine, and we know the volume that we've added because burette has volume measurements. We can say there's a 1-to-2 ratio between triiodide and thiosulfate. Therefore, there must be this many moles of triiodide. So we'll first look at that calculation from R2. So the number of moles of thiosulfate we would calculate first, and then we can go ahead and multiply that by the mole ratio. That's what I have this here to represent. And I'm going to say from the reaction. And we already said that it is 1-to-2, so I would fill in a 1 here just for an example and a 2 here. And that would allow me to calculate the number of moles of triiodide. Once I've obtained that, I can go back to reaction 1 because key will be to use the number of moles of triiodide so that we can identify the number of moles of H2O2 that must have been in the mixture originally. So my moles of triiodide, I'll use the mole ratio from R1 between triiodide and H2O2. That will allow me to get the number of moles of hydrogen peroxide. That's my goal for looking at reaction 1. Once I know how many moles of hydrogen peroxide were in the sample that I weighed, I can determine what that mass of hydrogen peroxide must have been and subtract it out of the total mass of my sodium percarbonate sample. And then to get the final value of the mole ratio, which will allow me to actually find this value of N, I can use the ratio of number of moles of hydrogen peroxide to number of moles of sodium carbonate. And this whole mass subtraction will allow me to isolate the number of moles of sodium carbonate that must have been present in the original sample. So that's for the first part of the experiment. There's also a second part of the experiment where we'll look at a mixture of sodium nitrate and sodium chloride. So this is not like the previous one where it's like a attached molecule to another molecule. This is just we took two solids and mixed them together in some ratio, and you have to figure out what that ratio was. The format we want you to actually do this analysis in, the end goal is that you could figure out the mass percent of sodium chloride in the mixture. So we'll take our solid sample, we will dissolve it in water and make a solution. And once we get to that point, each of these compounds should have dissolved and created a variety of different ions. So we will definitely have sodium ions. Those are not going to be important for our characterization. We will have nitrate ions, also not going to be important for our characterization. The key is going to be the chloride ions present in the solution, and that is because we have a strategy to actually make a product with chloride, and that is reacting with silver ions. When chloride and silver come into contact, they make a solid precipitate of silver chloride. And this is a really useful reaction. We could, theoretically, just weigh the amount of solid that precipitates out. But because of water being present and using such a tiny amount of silver and so on, it might be a bit tricky to actually get an accurate value. So we're going to use a different strategy. So that would be a gravimetric analysis. What we're going to do instead is we're going to add the compound K2CrO4, potassium chromate, and that is an indicator. The reason it is an indicator in this context is because silver ions, when they don't have chloride to make a precipitate with, it will react faster with chloride. That's kind of the key there. Then we'll have a really small amount of chromate around that could form a compound with the silver. And so we get this red-orange color when there's like one excess drop of silver present. We get the solution to turn red-orange. And so this is to kind of visualize that. Initially, we have a clear solution, and we would have weighed it. So that's really key right there. We weigh our solution that just has water and the mixture of solids before we add any of the silver. I think we would have already added our indicator at this point too, but because there's no silver for the chromate to react with, it remains clear. Then we start adding our silver compound, which is going to actually be silver nitrate. But again, remember, nitrate is not involved in the reaction, so we can ignore it. So at some point, we'll notice an additional drop turns our whole solution red or red-orange, and that is when we will stop because we don't want to add any more. So we'll take the mass of the final solution, and that will determine the amount of silver that had to be added. So we're going to use the known concentration of the silver nitrate solution. So that's here. We'll use the known concentration of silver in solution to determine how many moles of silver must have been in the solution. And that will allow us to backtrack because of the 1-to-1 ratio between chloride and silver in the reaction to make silver chloride. That will allow us to calculate the moles of chloride. Once we know the moles of chloride, we know the moles of NaCl. There's one chloride for every NaCl molecule. So that could allow us to determine the mass of NaCl and divide it by the mass of the sample that we measured at the very beginning so that we can get a mass percentage of the mixture for our analysis. So a lot of different strategies here to characterize the stoichiometry of a solution. Hopefully this helps with your analysis at the end.